Let's take a look at another example. We want to determine if this set of vectors forms a basis for R3. Okay, so again, we have to check two things. We need to check if the vectors are linearly independent, and we need to determine if these two vectors span all of R3. So as we saw in the last example, we can do all this with only one matrix. So I'm going to call the matrix A. Okay, and actually, let me write out the matrix first. So the matrix I'm going to use to do this, the vectors are going to form the coefficient matrix, -3, -2, 7, 1, 3, -7. In the augmented part, to determine if the vectors are linearly independent, I would put 0, 0, 0. I'd be interested in the homogeneous equation. Again, we usually don't write the 0, 0, 0. You can if you want. There's nothing wrong with it. But it's not, we know the 0, 0, 0 will stay 0, 0, 0. Okay? But what I do want is I do want to know if these vectors span R3. So I do want to determine, one way to determine that is if these vectors, if I could write a basis of R3, specifically the standard basis of R3, as a linear combination of these vectors. So the standard basis for R3 is ijk. So vector I in R3 is 1, 0, 0. Vector j in R3 is 0, 1, 0. And vector k is 0, 0, 1. All right. So I'm going to get this into reduced row echelon form. It's going to tell me everything I need to know about whether these two vectors are linearly independent, and if these two vectors span R3 by telling me if these two vectors, if I could use a linear combination of these two vectors to express each of these three vectors, each of the vectors in the standard basis for R3. Okay? So row 1, -3, 1, 1, 0, 0. Row 2, -2, 3, 0, 1, 0. And row 3, 7, -7, 0, 0, 1. Okay. So what I get once I get this, transform this matrix into its reduced row echelon form. Row 1 is 1, 0, 0, 1, 3/7. Row 2 is 0, 1, 0, 1, 2/7. And row 3 is 0, 0, 1, 2, 1. The augmented line comes after the second column. Okay? All right, so let's take a look at this. Let's first determine if the vectors are linearly independent. So for linear independence, I don't care about any of this. Okay, I just want to know, can if I had 0, 0, 0 in the augmented part, would I have only one solution or would I have infinitely many solutions? And I know I have at least one solution. X equals 0, y equals 0, right? In this case, though, that's all I have. I just have the one solution. I don't have any free variables. I have only two non-zero rows, and I have two columns. So I have no free variables. So the vectors are linearly independent. These two vectors are linearly independent. Okay. Now let's see if they span R3. So in order to span R3, I need a linear combination of these two vectors to equal to this vector, and a linear combination equal to this vector, a linear combination equal to this vector. Okay, so if we look at our equations, in the last row here, I start with 0, 0, and then over here, I get a 1. That means no solution, right? In other words, I can't solve for this this vector. Okay, I can't take a linear combination of these two vectors and get vector 1, 0, 0. I cannot get vector I. Okay, and actually the same is true for J and K too. Just looking at that last row and each column in my augmented part and term, I get 0, 0 on one side and 1 on the other, or 2 on the other, or 1 on the other. And each one of those would mean no solution. So not only do these vectors not span of all of R3, they actually don't span any of the vectors in the standard basis. They don't span, I cannot express I or J or K as a linear combination of these two vectors. So no, the vectors do not span R3. In order to be a basis, the vectors need to be both linearly independent and they need to span R3. This set of vectors are linearly independent, but they do not span R3. So the vectors are not a basis for R3.